Hello, everyone, and welcome to this PV Magazine webinar, How to Effectively Procure Energy Storage in 2023. Effectively procuring energy storage is a real challenge today. Automotive buyers are dominating demand for the lithium-ion market, and battery prices have started increasing for the first time. To make matters more challenging, not all battery manufacturers are equal. Engaging new suppliers can carry additional commercial and technical risk. In this PV Magazine webinar, we'll offer a guide to navigating those risks as a buyer of energy storage systems. Attendees today will walk away from the webinar with an improved understanding of the current and upcoming storage supplier landscape. Our presenters from Clean Energy Associates, Brandon Blair, Energy Storage Engineer, and Cormac O'Leary, Senior Manager of Market Intelligence, will walk participants through the energy storage trends from the supply chain and market perspective, as well as system designs and technologies. CEA will also outline the best practices to keep in mind when selecting an energy storage supplier. Today's webinar content will include a regional storage supply chain market trend survey. We'll look at the US, EU, and China, including trends in raw materials and chemistry. We'll take a look at what the Inflation Reduction Act means for energy storage over the next 5 years. We'll look at some trends in novel technologies and lithium-ion alternatives. And then we'll also examine design trends in cell form factors, thermal management, augmentation, and more. Finally, we'll take a look at best practices for choosing an energy storage supplier. That'll be followed up by question and answer, and questions can be submitted during the live webinar in the chat window. I'm your moderator today, Ryan Kennedy, editor at PV Magazine USA. And we'll like to start with a poll. I'd like to invite Cormac and Brandon here to join us, and we'll go ahead and start with a poll before we start our presentation here today. Welcome.
Thanks, Ryan.
Hello. Thanks for having us.
Just a little background on our presenters today. Cormac has been in the industry for over 15 years, working in lithium-ion batteries. He was the founder of Electrios Energy, a lithium-ion industry consulting firm based in Hong Kong. And his consulting work spans the entire lithium-ion battery supply chain, from metals, mining, material refining, cell production, and pack integration. He holds a PhD in chemistry from Northeastern University in Boston. Brandon Blair, Energy Storage Engineer, began his career in energy in 2014, and he's accumulated numerous certifications with experience across many phases of project development in PV and energy storage, from residential through the utility scale. He possesses both field and desktop skills, including project management, business development, design and engineering, commissioning, and O&M, with deep knowledge of the NEC, UL listings, NFPA codes and standards, and safety. So I'd like to welcome you both again today to the presentation. Thank you.
Great to be here. Thanks.
Yes, excellent. Thank you.
And it looks like we have some poll results here. So I don't know if you guys want to review those, and then I'll hand it over to Cormac to start.
Yeah, that's great. In the interest of time, I think we'll push forward and we can get back to you when we get some more input in on the poll towards the end.
Great.
Okay. Okay, so as Ryan stated, I'm Cormac O'Leary, Senior Market Intelligence Manager with Clean Energy Associates, and we will be, myself and my colleague Brandon will be doing a two-part webinar. The first part I'll take, which will be in light of recent developments in the US regarding lithium-ion battery production, cell and supply chain, and best energy storage. I'll be giving updates more focused on the US market, including material supply chains and market trends and updates. And then in the second part of our webinar, Brandon will be introducing the best procurement strategies, best safety and warranty, and augmentation strategies, followed by RFPs and purchase dynamics. Okay, so to begin with, I'll discuss the domestic, meaning US and Canada, North America battery material supply chain. So first, I'll begin with some of the work we've been doing in CEA, which is forecasting installation volumes, because you need to know how much material is required in the supply chain to meet future and current demands, as demand for lithium-ion batteries has really exceeded everyone's expectations in the last 2 years, and growing forward. The adoption of electric vehicles and energy storage onto the grid and residential also has really put a strain on the current lithium-ion battery supply chain. So we can see there's going to be at least minimum a 12x growth between now 2022 and 2030 in terms of installation volumes in the US. And yeah, as you can see, in a relatively short period of time, the installation volume was going to triple between 2022 and 2025, meaning in the next 2 to 3 years, the US is going to require a significant increase in cell production, as well as cell material availability. And the key driver to all this is the adoption of electric vehicles. It's really pushing the entire lithium-ion battery industry and straining the industry and supply chains. And we have looked into this in great detail here at CEA, and we have, as you'll see in the oncoming slides, we're hopeful that the US could be self-sufficient domestically in the near future. And what's spurring that also, it's really been a big help to the industry, is the recent Inflation Reduction Act, the IRA, which provides attractive credits for energy storage in terms of hybrid and standalone, but also cell production, module production, and material production and chemical refining capacity. So here's a current view of the current status of the US lithium battery material supply chain. Realistically, the US supply chain is in its infancy. There's very little ore mining, for example, in the US in terms of lithium or graphite production, if we're talking about synthetic graphite. And this situation is quite similar for cathode production, cathode active materials. We call it CAM or CAM in the industry. Right now, the US has to build the capacity quite quickly to reduce reliance on foreign supply. What we have seen, though, is the US has a rich history in separator production, and the capacity exists. We have relatively high electrolyte production, and that is because of the large Panasonic facility in Nevada, which requires a lot of electrolyte. Electrolyte doesn't ship well also, so mostly has to be produced domestically. And we envisage that the US will surpass 50 gigawatt hours of cell production this year. And to continue that growth, we're going to have to cut down on our reliance of imported raw materials. So, just how reliant is the US on lithium-ion cell imports? Well, if you look on the left-hand side, we can see that the current status is that the US is self-sufficient on cell production. In fact, the US is the second biggest manufacturer of lithium-ion battery cells outside China as a country. And that, again, is mainly down to the Tesla-Panasonic relationship. but there's other capacity, Asian capacity, such as LG Chem and SK Innovation coming online relatively quickly, which will really push the total production capacity cells in the US significantly. And if you look on the right-hand side, where are all these cells going? Well, we can see that for EV production, domestic production more or less mirrors domestic demand for electric vehicles, and BESS installations mirror the US battery imports. So that means that the US is close to 100% reliant on battery energy storage imports to fulfill demand. And that's something that we're going to have to address in the near future to meet some of the requirements that are stipulated in the Inflation Reduction Act in terms of the origin of battery raw materials, including lithium, nickel, cobalt, graphite. And what's also notable in the US in terms of end-use demand is the ratio and the percentage of that demand that BESS actually it takes up. It's close to 20%, which is quite significant. When you look traditionally at battery demand globally, BESS makes up a very small portion, but because the market's so dynamic in the US, a significant portion of lithium-ion battery demand will be going to BESS applications as we move out towards the end of the decade. So this is a high-level overview of how we see the growth of the US lithium-ion raw material supply chain. And we looked at the key materials, namely lithium and graphite, and CAM production. So that is combining lithium with nickel, manganese, cobalt, or iron phosphate to make lithium iron phosphate. This is a refining step that has to be which also has to take place within the US. And as you can see in 2022, presently, as shown previously, there's very little capacity in the US to satisfy the oncoming demand. But the US is quite rich in lithium resources, which I'll get into a little later in the deck. But there's a huge amount of projects online and coming online in the US for namely in geothermal brines in California, for example, or clays in Nevada. And if we just look at all the projects, which are over 50 projects in the US, there'll be significant, if all projects are successful, there'll be a significant amount of lithium chemicals available domestically. As you can see, graphite is in terms of projects is a little lower and not quite the amount required for the cell production if we look at 2025. But graphite production is something that scales and can scales quite quickly. So if you look out to 2030, we can see the graphite more or less mirrors the cell production. And we still see excess in terms of lithium production, but we finally see CAM production, which is going basically from zero in 2022 to perhaps these numbers on the left-hand side are in gigawatt hours, perhaps greater than 800 gigawatt hours based on announced plans currently by credible industry players in North America. So as I was mentioning earlier, the US and Canada are quite rich in lithium resources, and we can envisage that there could be over 300 gigawatt hours of lithium carbonate equivalent production in the US by 2025. And regionally, this capacity is distributed between the majority within the US in terms of projects and Canada, just about 40%. We can see what we can see coming online quite quickly is the hard rock, which is spodumene, and this is the major source of lithium globally at the moment, coming from Western Australia, where hard rock is processed to lithium carbonate. Canada is quite rich in hard rock deposits also, And a number of credible players are establishing mining projects in Canada, including restarting former lithium mines and brownfield projects also. And we expect this capacity to come online quite quickly. These companies are experienced in processing hard rock. They can process it to spodumene concentrate, which is about 6% lithium oxide in the ore, and finally refine it to lithium carbonate. We see brines, and there's huge brine resources in California under the Salton Sea, for example, amongst other places. These projects rely on untested direct lithium extraction technologies. Each project requires its own specific type of DLE technology, and we could see that there might be a delay in these projects coming online. So even if we disregard the brine projects, hard rock projects will be generating more than enough capacity for the lithium carbonate demand in 2025 within North America. Another possibility is the clays in Nevada, which Tesla mentioned in their battery day in 2020. So in terms of percentages of lithium, the clays are a little less rich in lithium, but because they're in clay form, they're easier to process. And you can process them either using direct lithium extraction technology or traditional solvent extraction technology. And we can see that clays could come online quite quickly as well, depending on the process of choice. And what's really noticeable for the US, as although US itself is not a big lithium producer at the moment, the top two companies in the field, Albemarle globally and Livent, have a number of operations in South America, Australia, and China, and they're bringing their expertise back home to produce battery-grade lithium chemicals here on US soil. And I believe that these projects can come online quite quickly also. So one of the choke points could be the cathode active material capacity. As I said, that doesn't exist in the US at the moment. But based on the IRA and many other incentives within the US, major cathode makers have announced plans and site-selected locations within North America, mostly in Canada, to produce cathode active materials. And some of the site selections are in Ontario, for example, which is close to the automakers in the US, where they will also have their battery plants. So the CAM producers are choosing to locate in Canada for number of reasons, most notably ESG reasons. There's an abundance of renewable energy in Canada. There's access to the raw materials, lithium, nickel, cobalt. There's a large nickel projects currently operating in Canada, not directly to supply the battery industry, but can be upgraded too. And the existing nickel projects are undergoing expansions to cater for the battery industry. So some of the major cathode producers, such as BASF, Umicore, POSCO, have announced credible operations in North America and can bring on significant amount of CAM production in about 2 years, depending on permitting and the rest of that. But they've already built these plants before, but they're primarily focused on NMC, high nickel NMC, which will be for the automotive industry and perhaps the energy storage industry, depending on the chemistry of choice. But we're seeing the CAM plants cluster in the Ontario region for now. And just a quick note in terms of NMC and LFP, ICL is the fertilizer company, large global fertilizer company, the Israeli chemical company, and they've announced an LFP plant that they'll be setting up in the US. They've been made LFP for many years. They provide LFP chemicals to Chinese LFP producers. So this is also a credible announcement of a company that knows how to produce LFP. So for graphite, there's two types of graphite. You have synthetic graphite and natural graphite. Natural graphite is an ore body, which I mentioned earlier. Canada, Alaska have some, and Alabama have some rich deposits in natural graphite. And battery makers require both types of graphite, both synthetic and graphite, depending how they want to blend their anode in terms of performance, whether you want quick charge or you want long life. They blend the materials appropriately. Synthetic graphite is produced via byproducts of the petrochemical industry, and the U.S. has, as everyone knows, has quite large petrochemical industry and produces a lot of the raw materials required for producing synthetic graphite for lithium-ion batteries, and this also can be brought on quite quickly in terms of production capacity within the US and North America. And there's a number of players involved in both the natural and synthetic. Sierra Resources, for example, have built a natural graphite processing plant in Georgia, I believe. And once you mine natural graphite, you have to process it into the correct particle size and coatings that are required for the battery industry. So as a first step, what we're seeing in the US is the processing plants are being built where the raw materials can be either shipped from Canada or Brazil or some other friendly nation to the US and be processed in the US and made available to the battery manufacturers. So as a first step, we're seeing Urbix and Novanex and Anavion beginning to build out processing facilities. But there's not as many players involved in the graphite space as we see in the lithium space. But it's a highly scalable industry, although it's quite energy intensive. So the current, if we had just look at the US current battery cell capacity, again, the Tesla Panasonic venture is leading, obviously, the industry. It has very high, it's one of the biggest battery factories in the world, actually, and has nameplate capacity of about 37 gigawatt hours. And they're constantly expanding the production facilities there and making, Panasonic has made some new additional gigafactory announcements in the US. We see, but the theme is these battery manufacturers such as SK Innovation, LGS their facilities are tied to EV manufacturers, and we will really need to see some more credible announcements in terms of battery production for the BESS industry, which have a slightly different requirements to the EV cells. Move on. So looking out to 2025, there's most of the announcements are focused on most of the industry announcements are focused on EV battery cell production, and so we can see on our view graph here that looking out to 2025, our total, we're just about 300 gigawatt hours of production capacity coming online in the next 2 to 3 years. And we evaluated the announcements in terms of permitting, environmental issues, funding, who are the players involved, who is there offtake agreements in terms of cell supply. And after critically reviewing the data, we still see there'll be significant production in the US by 2025. However, as I stated earlier, the majority of cell production is tied to EV electric vehicles. And so the chemistry of choice for, as we know, for electric vehicles is NMC, high nickel NMC moving from 622 to 811. and accommodating, as we look out, graphite and then graphite plus silicon. But the region we're looking at for our energy storage business is doesn't have the same type of requirements in terms of energy density and fast charging as electric vehicle cells. So most of the plants and our customers and clients are interested in lithium iron phosphate. And the big question is, how much more room is there available to expand the energy density of lithium iron phosphate cells and energy storage units, BESS systems itself? So the data we have here, for example, is for cell data. So 200 watt hours per kilogram is advertised by certain LFP manufacturers, but as we know, that's not really accurate of the system in the field. What we're seeing in the field is cells at about 160 to 170 watt hours per kilogram or less, maybe even 150 to 170, depending. But we will see as we look out in the next 3 or 4 years that there will be increase in the energy density of the BESS systems itself, so using LFP or LFP variants, which we have highlighted here. We have lithium manganese iron phosphate is one potential candidate, and we have lithium nickel manganese oxides. The spinel type structures are really attracting attention in the industry in terms of increasing gravimetric energy density. So we see LFP remaining as globally as the cell of choice for BESS energy storage systems. But as I mentioned earlier, the US battery announcements and industry is more or less focused on electric vehicles, and they're working with NMC type chemistry. But we've also been monitoring what we call the mid-size battery manufacturers, which don't have particularly strong ties to OEMs, electric vehicle OEMs, and but these companies are not startups. They've existed for many years. They have provided quality cells. So if you look at Enersys, for example, have the most lithium-ion cells in space at the moment. So high quality cells based on NMC chemistry, and these companies are also interested in becoming gigafactories and building out their capacity based on their existing business models and a new business models, which is really catering to the BESS market using chemistries that they know well, such as NMC. And we can see as we move right, there's some newer players entering the field. Microvast, not exactly a new player, 20-year-old battery company, but will vary their products depending on the customer demand, NMC or LFP, where we have Ornex Energy, one currently announcing building a gigafactory, which is solely focused on an LFP variant or their own version of LFP, which they have IP. It's not entirely clear, but it's a very high energy density chemistry, which they apply to electric vehicles, but also have a energy storage business and plans to roll out some very large energy storage systems. And these are companies we're keeping an eye on as potential domestic suppliers for our BESS customers. So in terms of BESS market updates, one of the most significant events that could be in battery history really is the IRA incentives, which really made domestic production of battery materials, our cells, and BESS systems attractive to set up in the US. You can see here the production credits, especially the $35 per kilowatt hour production credits for cell manufacturing is a very enticing incentive. And even battery modules, you get $10 per kilowatt hour. So you could, in theory, source your cells from elsewhere, assemble in the US into modules, and be entitled for this credit. But it's not just downstream. If we look upstream, there's incentives also in terms of electroactive materials. That is the CAM materials I was discussing earlier. There's credits up to 10% of the total cost of production. And this applies to the critical minerals such as lithium, nickel, manganese, cobalt, and graphite. There's also credits in terms of production credits, in terms of establishing factories in the US, both battery factories and recycling factories, for example. But you have to meet certain labor requirements, and there's a $10 billion limit on these tax credits. So, but that's not the only source of funding available. The loan office have some significant funds available for battery supply chain projects within the US, and also direct loans can be applied for. But the biggest factor that will determine the success of the US domestic battery supply chain is the $35 manufacturing credit, which we dive into a little here just to see what's the difference, the current difference between a cell sourced in China, for example, or a cell manufactured in China, a cell manufactured in the US, and a post-IRA cell. So we can see on the right-hand side, applying the $35 credit per kilowatt hour, that the price of a cell could drop to $86 US per kilowatt hour post-IRA compared to 124.4 currently. This is a model system, not actual production numbers. But we can see if we compare the post-IRA to the China cell model, there's a huge difference in price that would make it impossible for outside suppliers to undercut in some way US manufacturing. And where we see the big difference is, and this is for an LFP cell, some of the bigger differences we see are in terms of the cathode price. If you're manufacturing LFP, which doesn't involve nickel, cobalt, or manganese, we can see there's little variance in the cost between China, US, post and current, but we see a difference in terms of active materials, the graphite, electrolyte, which could potentially drop the cost. This is for the manufacturing cost of bill of materials, which is a small percentage. It's not $35 per hour, it's about $3.5 US per kilowatt hour. So on top of the 35 in terms of bill of materials. And I'd like to invite Brandon now to go through our procurement strategies.
Alrighty then, thank you very much, Cormac. So we'll jump into some storage supplier procurement considerations and diving in. So in the past, it may have seemed like we were in the wild west of energy storage procurement and developing of our energy storage systems. But fortunately, as the industry has matured, as we've evolved and we've learned from some important lessons learned, we now know that there's a lot of considerations that we need to be accounting for earlier on in project development, that we can't just worry about and kick the can downstream and to worry about these issues down in later project phases. So with batteries, we want to look at product warranties, availability guarantees, capacity guarantees, augmentation strategies. We want to consider many more things than just who are we actually buying the batteries from. And so first and foremost, one of the topics I'm going to be routinely touching back on over the next few minutes is the importance of discovery questions for a given developer or an entity that's going to be deploying energy storage. They need to internally determine what their development strategy is in terms of their pipeline or their existing completed installations. Are they dipping their toes into the industry for the first time? What does it look like in terms of their risk appetite? So that developer, that entity needs to do a little bit of internal discovery. That way they know what to look for when they're asking for a particular vendor to supply solutions to their project. So it could be very highly variable depending on the site or the size of the project. So first and foremost, we need to identify what are those developer-specific scorecard criteria when we're evaluating our vendors. So it's not just as simple as who we're buying the batteries from, but we have many different components with our energy storage system, many critical components such as the controls, the rest of the balance of plant, We have many different stakeholders in terms of the PCS or the EMS provider that's different from the integrator or the battery supplier. We have the long-term warranties, the long-term service agreements. So we have many different angles that we need to consider. And so we want to apply good principles of quality and risk management to be proactive, to make sure we're going to prevent issues before they happen. We want to prevent those fires instead of putting out the fires. So with the procurement stage, we want to be thinking about all these different critical areas. That way we're not going to be dealing with what does the degradation and the augmentation challenges look like after we've already selected the vendor. So to deploy a safe, reliable, high-performing system during the procurement stage, we need to be thinking about these longer-term implications to our system. First and foremost, if we're looking at a vendor, we need to consider the vendor profile. We have the financials, the project history. Is there anything that differentiates that vendor, setting them up for a good competitive edge against other vendors? What is it like for that product integration into other suppliers? Are we looking at a turnkey product that's start to finish, one throat to choke solution? Or are we going with an approach that's a little bit more piecemeal, where we have to have some application engineering to piece together, this is the best component, this is the PCS. So it's going to be some variability in the scope of the integration and how does it play well with other technologies. In terms of financials, we'll want to look at the product quality. What is it like for the guarantees, financial backing, JVs or recent mergers and acquisitions? Project history, where the project's located. Does the developer care about existing completed installations in a given territory of the states, for example? Project sizes. Things that might differentiate that vendor from other vendors, including revenue realization controls, adaptive warranties, software controls for predictive failure modes analysis. So we want to start by looking at the vendor profile that itself. What is the vendor details when we're considering who to procure the batteries from? In addition, I want to start by talking about the safety aspect, because this is a very important aspect with our industry. We do have battery incidents. These are low frequency, but they are high hazard in terms of high capital and high hazard to our first responders. So first and foremost, safety is a toll gate, a critical pass or do not pass that could be an instant elimination to potential vendors if they do not align with the proper listings and the testings. So we have an assortment of safety listings from the factory, from the manufacturing line, from the cell, the module. We have listings that have to do with electromagnetic compatibility with the interconnection. We have safety at the system level. So anyone that's dealing with codes and standards know that as the industry evolves, there's more and more codes and considerations to contend with. And so it's important to do due diligence into the AHJ. So when we're early on in our procurement stage, we're identifying the AHJ for our sited location, and we're doing due diligence to determine the standards and the expectations that that AHJ, authority having jurisdiction, is going to be enforcing. We do not want to procure a system and install a system and then realize from a final inspection that that system is not listed to the latest standards that that AHJ expects. So we highly recommend due diligence early on, making sure our system is safe, it's listed to the expectations of that jurisdiction. Contact that local fire department or that building department, making sure we know that the system is listed. The procurement process is going to have the developer looking into the vendor to determine that the vendor has the latest safety reports that they will release to that developer that then can release to the AHJ. So thermal runaway considerations, safe fire safety system design, using the latest best practices. The codes are constantly changing, so we want to make sure that the AHJ that we're dealing with, where are they in their adoption or enforcement of given standards. In addition, with a longer term supply agreement that we'll kind of touch back on in a few minutes, if we have a large supply agreement with a particular product, it's important to make sure we have flexibility. That way we're not locked into a given product that may have a serial defect in a few years. So with longer term supply agreements, it might be beneficial to make sure that we have flexibility in the products we select in case there arises a quality issue with a given product in a couple of years. So safety, very important topic. toll gates, do not pass go if you do not have the right safety listings. And we want to compare that to the AHJ requirements. In addition, warranties are very important. Again, we want to talk about our internal discovery about what is the developer's strategy. Are they a long-term owner operator, or are you more like a EPC, you're flipping it? So depending on the stakeholder position, the warranties will be more or less important. But given that these systems are long-lasting, years and decades worth of operation, we do want to do due diligence into our warranties, taking a look at what are the standard defects, what are the protections, what are the limitations. If we have, as I mentioned before, a large long-term supply agreement, we might be able to leverage that large portfolio of capacity. We might be able to leverage a large system capacity to negotiate better warranty terms. However, we have seen in the past that generally you need to have a pretty sizable portfolio, 100 megawatt hours, up to, even as minimum as 1 gigawatt hour, in order to be able to have that size to leverage into better warranties. In addition to warranties, we have performance guarantees, sometimes referred to as capacity guarantees. Generally, we want to make sure early on when we're looking at procurement that these are going to correspond to our actual use case. We want the performance guarantees to be reflective of what type of battery, how we're using it, how we're cycling it, the temperature, the site conditions, the energy throughput. We want to make sure we're aligning the performance guarantees with the actual use case for our given site. So some best practices, we want to see warranties including workmanship warranty and EPC performance wrap. That way we're going to protect the developer if there's any kind of negative interaction between the finger pointing between the EPC and the OEM, the cell OEM. So workmanship warranty, EPC performance wrap will help buffer that. Integrator's warranty, depending on the type of integrator that we're looking at. Is it a turnkey solution, or is it a highly customized system with multiple different components and different stakeholders? And we want to make sure we have a complete wrap for accountability. Engineer of record, we would like to see an error and omissions insurance, professional liability insurance for any mistakes potentially made there. And then recognizing that battery PCS limited warranty is generally about 5 years, but there's usually provisions for extended warranties in the 5-year increments. We often see that. They can potentially be 20% of the initial cost of the warranty. We're going to touch back on this topic with the RFP dynamics in a few minutes. But we want to have good clarity in the dynamics of how the pricing scales with the performance warranties and the limited warranties. We want to see that level of protection with these long-lasting systems. So touching back on what we talked about with the vendor profile, why it's important to start by looking at the vendor, the different dynamics of that vendor with the projects and the financials. In terms of the supply chain itself, there's a lot of variability in the different strategies between different integrators. Up the supply chain or down the supply chain, it's important to look at whatever integrator you're looking at, whatever vendor you're looking at. Are they going up the supply chain? Are they securing capacity with a certain cell OEM? Or are they diversifying their portfolio? Are they allowing themselves the flexibility to select multiple different cell OEMs to deal with any kind of supply chain volatility, which then can provide extra flexibility to the developer? Maybe the developer will be able to choose what cell they want their integrator to use. So it's important when you're looking at the system integrator to identify where they lie within the supply chain, because it's highly variable. Certain integrators may not be offering the EMS SCADA. They may be taking that under their umbrella. So depending on the scope of the system integrator, we might have more or less responsibility as the developer. In addition, battery degradation is a very important consideration with developing these systems. We need to account for the degradation as it corresponds to our actual use case. We have multiple different strategies to account for degradation. We can go with a larger initial overbuild. We can have planned augmentations. There's pros and cons to each strategy, but again, in the procurement stage, we want to be looking at what the strategy is. What is the vendor's approach to this issue that we often see with lithium-ion batteries? If we're considering a non-lithium-ion technology, what does the degradation look like there? That way we can actually compare apples to apples. In terms of utilities and IPPs, just the nature of the use case can determine what our approach with the augmentation strategy will be. With the utility agreement, we have to maintain often a minimum capacity. So in that case, we have to augment those systems. However, if we're an independent power producer, we may not have to augment. In that case, it becomes a cost to benefit ratio where we need to determine if the cost of augmenting is going to gain additional revenue that's going to make sense to perform that augmentation. So it's a little bit more discretionary, even based off of the interactions with the utility or the independent power producer. And so, as I mentioned earlier, with the main strategies between overbuild and designed augmentation, overbuild, we have more of a capacity initially, so we have a higher CapEx, or if we're going to intentionally augment throughout the life of the system, it'll be lower CapEx initially, but then we're pushing that onto the OpEx. And so we want to make sure that whatever our strategy is, it corresponds to our internal discovery developer profile for our objectives with that project. What does it look like for that EPC to go back potentially? So we want to make sure that we're coordinating all these different strategies as early on as possible. And so the last few minutes, I want to go through some specifics with the RFP and purchase dynamics. We have two major philosophies with project development. We have a project level planning. We also have a portfolio level planning. And the main point that I want to make on this slide is just we've seen an increase in developers going for a master supply agreement to capacity lock, to secure capacity for a portfolio of projects and leveraging that risk against inflation or other price volatility spikes. So we're seeing a little bit of a shift for developers preferring a larger agreement. And it's interesting because we've even seen this with developers that haven't even completed an initial installation yet. So there is some risk with that. And there's pros and cons to each style approach, where if we're going to do RFP, we're going to solicit bids per project. Well, then we might be dealing with a little bit of a risk with supply for future projects. So it again depends on the specifics for that developer's profile, but we have seen an increase in the master supply agreements. And interestingly enough, we've seen an increase in supply agreements, not just from the developer onto an integrator, but also the integrators securing supply agreements with their OEMs as well. So whenever we're looking at RFPs, we're looking at multiple bids. What we want to do first and foremost, we want to levelize the bids. We want to have a way to standardize all of the different bids and vendors against each other. That way we can properly benchmark. And in order to do so, we might have to gather quite a lot of information. We might want to develop some standardized spreadsheets. We're collecting information on that long-term service agreement, the costs, the augmentation costs, the degradation profile. That way we can properly benchmark the different bids against each other. So levelizing is one of the most important first activities to do when we're running RFPs. We want to do levelizing activity, that way we can identify missing information and identifying critical elimination factors such as safety. We can quickly shortlist our bids to determine what our most important selection criteria are. In addition, same thing as I mentioned before, we want to look at the vendor profiles with our bids. What does it look like for their OEM flexibility, bankability, installation history, etc. And additionally, we also have different pricing strategies. What does it look like for, is it a pricing index style? How long until the bid, the quote for a project, how long is that valid? When do we need to get the final price? What's the floor? What's the ceiling? So the pricing strategy is also another consideration when thinking between an RFP or a master supply agreement, or even spot pricing per project. Another assortment of additional considerations and areas of risk within contracts. At the RFP stage, we might not have granular information of these different areas. However, we still do want to look into these areas as early as possible in our procurement. There's significant risk if we do not. There's long-term service agreements. That's a long marriage with that project site. So we want to make sure we're looking into, do they have service availability domestically? What are the terms and conditions with the O&M? Do we have a third-party affiliate provide that service, or are we going to rely on that vendor? So numerous areas of consideration when we're looking at RFPs and contracts as early as possible, as I mentioned before, with quality and risk management, looking at these areas as early as possible in our procurement strategy. And so in summary, to wrap everything up, the selection criteria is going to be highly specified and customized to each individual developer or entity that's deploying an energy storage system. So you must do the discovery, you must identify and tailor these criteria to your specific approach. And once you do that, once you have an identification of that, you can put together a scorecard to start to benchmark different suppliers against each other based on your use case, your profile. The different weighing of these areas might be highly variable between the different developers, but we want to find quick fail fast points where this is an absolute critical selection criteria, or this is not as much, based on our risk appetite, based on our completed history. That way you are able to better perform procurement on different vendors. That way we're moving away from the days of the Wild West where anything goes. So that about wraps it up. I guess, Ryan, I'll pass it back to you. Thank you.
Excellent. Thanks, Brandon. Great presentation from you both. Now we have a little time for some Q&A from the audience. So I'd like to invite Cormac back on, and we'll ask a few questions. So first, from the audience here, audience member was wondering, do the IRA incentives, do they favor EV battery manufacturing versus BESS, or is it sort of an even pegging there?
Yeah, can you hear me?
Okay,
okay, great. Yes, there's a little bit of a slight favoring towards EV batteries, since the IRA addresses many parts of the supply chain, but and in terms of critical materials, hidden in the fine print, you can see it's kind of directed towards cobalt, nickel. Fortunately, both chemistries share lithium, which is a critical component, and graphite, just slightly, but BESS will be able to take advantage of many of these IRA credits, and you get the same $35 credit whether you're making an EV battery or BESS battery, for example. And I think the IRA might push more towards NMC, but I think it'll provide NMC with a unique opportunity in the US in the energy storage market also.
Great. And another question from the audience. Do performance guarantees include the ability to follow grid signal to deliver or absorb energy, such as in frequency regulation services?
Usually performance guarantees are more aligned with a capacity or availability guarantee, where based on our use case, we guarantee that we're going to have a certain performance of capacity to meet those requirements. So that level of a specific, that might be more or less with looking with the EPC warranty. The performance guarantee is usually more from the battery OEM or the vendor, looking at the capacity availability for the system to perform services. So like a 98% availability for the system.
Great. And we had a handful of questions about sort of the environmental side of lithium. Wondering if you could talk a little bit about the differences in environmental impacts of different extraction types. And then we also had some questions on recycling. Do we have recycling capacity set up? Can we create a circular economy with lithium? And if we don't have those capacities yet, maybe how do we get there?
Yeah, sure. So regards ESG issues, yes, mining is always going to have ESG issues. So traditional mining is blasting, digging holes, requires a lot of fuel and energy just to do that process step, where US, which is leading this industry in terms of geothermal brines, has a unique opportunity you can produce lithium from geothermal, which is a liquid, from geothermal brines by selectively removing the lithium ions from that solution. And so you pump the brines from underground, you pump them up, you can use renewable energy to power your pumps, for example. Our geothermal brines also are currently used in the US as power stations. So they power themselves basically. And so very low carbon footprint for geothermal brines. Less so as you move up towards blasting rock and hard rock, but with clays, you don't have to blast, or you can dig up the clays and process it. And there's a big movement in the mining industry towards electrifying mining equipment, that is digging equipment, shoveling equipment, transport equipment, trucks. It's part of every major and minor mining company's strategies. Hopefully you can really bring down the carbon footprint in the mining sector there. In terms of recycling, there's huge movements in the US towards building up battery recycling capacity. The person asked the question is right. The capacity does not exist at the moment. It's still being defined how to move forward with that in terms of how to process the recycled material. Traditionally, the process was shifting towards recycling the nickel and cobalt and lithium from the black mass, which is the recycled material, the material you get from crushing a cell. And now the movement in the industry is, instead of breaking it all the way back down to its initial components, to rejuvenate the cathode material. So that's the next step we'll see. So you recycle the cathode active material. So you don't have to go all the way down to reproducing that cathode material. You rejuvenate it and put it back into the supply chain. Only issue there is it'll have to be proven that it's as good as pristine new CAM material, but I'm sure that should be a step we can surmount. But the big focus in the industry is on recycling globally.
Yeah, if I can also jump in there, we also have a new listing, UL 1974, for second life batteries, in which we're starting to investigate potentially repurposing older EV batteries into energy storage applications. Of course, still passing the quality requirements to do so.
Great. And we had a few questions about alternative energy storage types. Wondering if you could comment on the efficacy or role of things like liquid metal batteries, flow batteries, and sort of that category.
Yeah, Cormac, I'll take a stab at that from a code and safety perspective first. So with any new emerging technology, I would also highlight the need to look at the safety and the listings and the testing that is done to verify that it is truly a safe technology. To date, we have limited code reference and standards for other alternative technologies. We expect that to change. So it's pretty lenient for other technologies. We are seeing revisions in making sure that this other alternative technologies are going to be safe. But right now, the overwhelming market share is with the lithium-ion batteries. We are seeing lots of interest from developers asking about alternative technologies, largely due to the supply constraints and the volatility with pricing. So we definitely see the interest. But as with any new emerging technology, it's important to make sure we're doing our due diligence, we're taking our time, we're establishing our quality checks, and we're going through to verify the systems are tested and listed for safety. Each individual new alternative technology has its own unique potential characteristics of safety or other considerations that we need to evaluate on a case-by-case and a fair level basis. Cormac, I'll pass it over to you.
I agree, Brandon. Yes, of course. The battery industry is evolving quite rapidly, and we are looking at technologies that aren't like 10, 15 years away, like lithium air or lithium sulfur, which is probably a bit closer, or solid state. We're looking at chemistries that are already developed. Sodium sulfur, will that find a role? We're addressing a market that's evolving at the moment, so the existing chemistry, we got vanadium flow batteries, we have sodium-ion coming online relatively quick as well. What we're looking at is addressable markets. Lithium-ion has a ceiling, how far out it can go in terms of energy storage and still being cost competitive. And so there's different applications for alternative technologies, and I think they'll all find a place. I don't think lithium's going to have its sweet spot over a certain duration, and as we move out to longer durations, we have the technologies already, and just finding a role and make them cost competitive. But for foreseeable future, we're still looking at lithium-ion, sodium-ion, sodium sulfur, and then as the question, liquid metal, for example, definitely has good opportunities in a certain part of the market as well.
Great. And I think we have time for one more question here. So I noticed on the chart, kind of looking into the future for energy density, we saw that solid state batteries were, way up at the top. So our audience member was wondering, will those be relevant in grid scale storage, or do you see solid state being mostly relegated for things like mobile devices and EVs? And I can ask, yeah, the question was from the audience, do we see solid state batteries, they were at the top of the chart as far as energy density goes. Do we see that as playing a relevant use case in grid scale storage, or is this more of like a mobile device and EV type application? And also, when do you see those playing a large role in the market?
So for me, I don't see it playing a role in the energy storage market. Initially, any new chemistry, as Brandon alluded to earlier, safety, there's many factors that be considered. It's going to take a number of years for the costs to come down in any of those chemistries. And what we're doing in energy storage is trying to get the lowest cost, maximum value. And I don't think novel battery systems will have a role until their costs really come down. They don't even exist yet, so that could be 20, 30 years away.
Cool. And we actually still have a good audience with us, so I'm going to ask two more questions and then we'll wrap it up. So I was wondering if you could, Brandon, maybe you could talk about the evolution of battery control systems over time and maybe some of the advantages of the current state-of-the-art control systems.
Yeah, so a little bit of an overview with our battery controls. We have a battery management system. Usually that's going to come from the cell OEM. So that's going to be proprietary to whoever is making the cell, or at the very least the module. And it's a little bit more of a simple software technology where we're just monitoring and maintaining the voltage, the temperatures of the cells at the module level. And then we have a larger overlay energy management system, which is more controlling when the system is being dispatched, its integration into the fire safety system. So as we've evolved, especially with the safety side of things, we're starting to see that water-based suppression is more effective with thermal runaway management due to its superior cooling effects. With thermal runaway and clean agents effective at putting out open flames, but in terms of fire safety and reducing the propagation of the thermal runaway, we really need to have a cooling effect. So we've seen some evolution with the codes and the safety with the energy management system incorporating water-based suppression. We're also seeing some inclusion of gas detection. Early gas detection is an indication of thermal runaway events before it's gone into the out of control exponential growth of the heat. So we have off-gassing that's a little bit earlier on in thermal runaway. So gas detection is a good addition for early safety measures. We've also seen some research, very new, based on water spray, not necessarily just flooding with a dry pipe connection, but we've seen water spray. And then in terms of software controls, we've seen a little bit more investigation into predictive failure analysis, in which we have EMS systems added on top, software systems added on top of the EMS to look at not only current voltage and temperature trends within the battery module, but also looking at a historical analysis to see if we have a slowly increasing average temperature within a module or a cell as more of a predictive measure of eventual failure. So the systems are getting smarter, and we're getting more robust controls than we used to have in the past, which is good. It's just making sure that we have the entire system wrapped and integrated and talking together nicely.
Great. And one final question from the audience. So prices have been increasing over the last 3 years, and it was a long period of price reduction in the past. The audience was wondering, when will it be forecasted that prices reach back down to 2019 levels?
I'd be a rich guy if I could predict that. But,
I was just about to say that's $1 billion question.
yeah, not anytime soon though. So I think it's just the supply demand imbalance. But as I showed during my talk, we see a lot of lithium capacity, which the prices are mainly increased due to the lack of lithium. There's a lot of nickel and cobalt because less cobalt's being used in cells available. The pricing is basically based on nickel. So the more lithium, the more lithium that comes online. With China's doing big push in creating domestic lithium supply, US and Australia is expanding some of their hard rock explorations. It's a little more difficult for in Latin America and Chile and other places to expand brine projects due to many issues in terms of environment and just the length of time it takes to produce brine, lithium from brine solutions. But it depends on the build out in the US and China. But for the next few years, it's going to be pretty tight in terms of supply and demand on lithium.
Great. Well, Brandon, Cormac, want to thank you both for your presentations today. Really insightful. And I want to thank the audience for attending as well. Thanks very much.
Thanks, guys.
Right.
Thanks.
Thank you. Cheers.
Yeah, and if you enjoyed the presentation today, be sure to check out PV Magazine. We have both a print publication as well as an online website. I'm editor for the USA website. If you scan the QR code hit there, we have a couple articles from this week. And we're also offering 10% off our subscription to our print magazine.
Thank you.
Take care, everyone.
Thanks very much. Take care.